the kinetic theory, the kinetic molecular theory of gases. The kinetic molecular theory of gases, simply we call KMT. The kinetic molecular theory explains about the behavior of the gases. It can give the physical observation of the gas, understanding about the gas, and behavior of the gas we understand. And also we study the physical properties like the pressure, the temperature, the volume, and the number of moles of the gas about the molecules we'll understand by using kinetic molecular theory of gases. This is a theory that gives about the idea about the mental picture of the gases. Based on this, we can study what are the real gases, what are the ideal gases. According to this kinetic molecular theory of gases, according to the kinetic molecular theory of gases, a gas consisting of the particles, those particles are atoms and molecules, which are identical. When a pressure is applied, when the gas is compressed, how the gas behave at a molecular level? What happened to the molecules when the gas is compressed? What happened to the molecules when a gas is compressed? If we want to understand how the gas behave at a molecular level, we should study this kinetic molecular theory, which is a mental picture, which enable us to better understand our observations. And it is the theory that elucidate the behavior of the gases, we say. So if you want to understand the behavior of the gas, first we have to discuss the assumptions and the postulates of kinetic molecular theory. So what are the assumptions and what are the postulates of this kinetic molecular theory of gases? According to this kinetic molecular theory of gases, a gas consisting of large number of identical particles, that's to be atoms or molecules, which are very, very small and so far apart, the average actual volume of the molecule is negligible in comparison to the empty space of the container. They are considered as the point masses. With this statement, what we understand means the gases have great compressibility property. That means if you assume that the volume of the container is V, the container has the empty space, and each particle present in the gas considered to be point mass. It is point mass, we should consider point mass. According to the kinetic KMT theory, the average volume of the molecule is neglected when it is compared with the volume of the container. So with this, what we can understand means the gases highly compressible. Compressibility properties are more. We can apply more pressure for the compression of the gas. So this is the statement which talks about great compressibility character. That means, so if you take the gas in the cylinder and by using the piston we can compress the gas because the molecule, average volume, actual volume of the molecule is neglected as you compare with the volume of the container. Now the second assumption, if you discuss this second assumption, the second assumption of KMT talks about there is no force of attraction between the particles of gas at ordinary temperature and pressure. The support for this assumption comes from the fact that gases expand and occupy all the space available to them. So best example, if you fill the gas in the balloon, since the molecules randomly moving or in the balloon, the gaseous molecules will spread when temperature is applied on this balloon, it can expand. That means here what we understand from this, between the gaseous molecule there is no force of attraction at ordinary temperature and pressure. So gases can expand and occupy the space available to them. Gaseous molecule, between that gaseous molecules there is no force of attraction. That means the second assumption talks about force of attraction between the gaseous molecules. Force of attraction between that gaseous molecule, there is no force of attraction. That means no force of attraction, we say. The third assumption talks about the particles of gas always in constant random motion. If the particles were at rest and occupied fixed positions, the gas would have had a fixed shape which is not observed. And if you take the container in this empty space, if you leave the gas in that, the gaseous molecules move freely, randomly. In random motion, the gaseous molecules will have, but each particle motion is state motion, we say state motion. In case the molecules are at stationary, the molecules are fixed, then it will get the definite shape. Since the molecules have the constant random motion and constant random motion, so it has no definite shape. The shape of the gas depends upon the shape of the container. Fourth assumption of the KMT speak about fourth assumption. The particles of gas move in all possible directions in straight line. During their random motion, they collide with each other with the walls of the container. The pressure is exerted by the gas. Result of collisions of the particles with walls of the container. That means the pressure is developed by the gas. P is equal to, we can write the force F upon A. Force upon A is the pressure, so due to the collisions of the gaseous molecules over the walls of the container, So with this fourth point, what we understand means, because of random motion and the straight line motion of the particles present in the gas, they apply the pressure on the walls of the container continuously, which is the formula, pressure is equal to force upon area. Now the fifth assumption talks about collisions of the gas molecules. If you assume that the gas molecule is perfectly elastic, and this molecule collide with the neighboring molecule, since the molecule has kinetic energy and it has a momentum, and the momentum can shift to other molecule. And again, this molecule and pushing that other molecule, colliding with other molecule, then automatically there is the momentum shift. There may be exchange of energy between the colliding molecules. Their individual energies may change, but the sum of the energies remain constant. And with this, what we can understand means, if you take the gas in the container, all the molecules do not have the same energy, all the molecules do not have the same kinetic energy, all the molecules will not have the same speed. So, and during the collisions, there is a shift of the momentum, there is a shift of that energy takes place, but the total energy of the molecules remains same. That what we call means average kinetic energy, we say. So that means the gaseous molecules follow the law of conservation of momentum and law of conservation. In case the energy is lost by the molecules, they can settle at the bottom, and so it will not show the gaseous property, we say. That means the average kinetic energy Ke of the molecules, Ke is equal to, kinetic energy is directly proportional to temperature of the gas. We can write. When temperature increases, the kinetic energy of the molecules increases, the motion increases, and the speed increases of the molecule, velocity also increases, and the collisions increases. Again, the temperature increases. The kinetic energy of the gaseous molecule is directly proportional to the temperature. This is average kinetic energy. Because all the molecules present in the gas container, all the molecules of the gas do not have the same speed and same kinetic energy, we say. That means at a particular time, different particles of the gas have different speeds, and hence they have different kinetic energies. So hence we have to consider average kinetic energy of the gas is directly proportional to temperature. When the kinetic energy of the gas molecule increases, the thermal energy increases. So these are the assumptions of KMT, kinetic molecular theory of gases, we say. And with this kinetic molecular theory of gases, we'll understand the physical properties of the gases.